All right, so today we're going to look at chemical nomenclature. That is, how to name chemical formulas, chemical structures. Okay. Now, this is not going to be. Ooh, sorry about that. It's not going to be an overly long video. However, it is probably going to be something you're going to want to watch more than once, or maybe pause in the middle and make sure you're keeping up. Okay. So let's jump right in. So here's the basics. Here's the basic thing that you have to know. Number one, the symbols in a formula come from the periodic table, right? We've talked about the periodic table. We know about the symbols. They're derived from the name of the element, sometimes the Latin name, right? So things like potassium is K because the Latin is kalium, all right? Whenever you're looking at a symbol, the first letter is always capitalized. The second letter must be lowercase. Now, this is really important, okay? If you are writing a formula and you have terrible handwriting and we can't tell, the difference between cobalt and carbon monoxide, that's going to be an issue. So make sure the first letter of the symbol is capitalized. If there's a second letter, it has to be lowercase, okay? Cobalt is CO, carbon monoxide is CO, but the capitalization in the second O is what tells them apart. The subscripts by the symbols are going to tell you how many atoms of each element are present. Okay, it's pretty obvious. So like CO2 has one carbon atom and two oxygen atoms. If you have subscripts outside of a parentheses, then they apply to all the elements within the parentheses. Just like in math, you're going to distribute that number. So here, all right, I've got 2 times an implied 1 and 2 times that 4. So I have 2 total nitrogens, 8 total hydrogens. I only have 1 oxygen. That 2 has nothing to do with the oxygen that comes after it. All right, the subscript always acts on the thing to its left. If I can't read it, I'm probably going to mark it wrong. Okay, so make sure that you take your time when you write these formulas. There are 3 kinds of formulas we're going to look at. There's molecular formulas, there are empirical formulas, and there are structural formulas. A molecular formula is going to show you exactly how many atoms of each element are present. It's going to show you what one molecule looks like. These are great for covalently bonded compounds, for nonmetal compounds, that kind of thing. Empirical formulas show the smallest whole number ratios of atom in a compound. And for ionic compounds, we always use the empirical formula because there is no molecule in an ionic compound, right? If I have salt, I have Na bonded to Cl. That's the formula we use, but in reality, it actually forms a cube, like so. And back here, there is an Na, like that. And this cube forms more cubes with other, like chlorine and sodium atoms. So ionic compounds are salts like this. They form these crystalline structures. And so we break them down into their simplest part, right? NaCl. Or here, right? NaCl. Or there, we have NaCl. So an ionic compound is always going to use the empirical formulas. It doesn't always show you how many atoms are present, okay? For example, C6H12O6. This is a molecular formula. It's glucose. I know it's a molecular formula because it's not reduced. The reduced version would be CH2O. This is the empirical formula of glucose. It's not glucose. It's just the empirical formula. So be careful there. If something asks you for empirical, or gives you empirical, that doesn't always tell you how many atoms are present. A structural formula is actually a picture, okay? A Lewis diagram or a Lewis diagram is the thing you're going to see most common, okay? But they don't have subscripts unless there are like molecular formulas involved. So if we look at molecular and empirical formulas, for H2O, the molecular formula and the empirical formula are the same, right? Because I can't reduce this 1, all right there. Once I have a 1 as a subscript, I can't reduce it any further. If we look at H2C2O4, and I said, okay, this is the molecular formula, can we write a different empirical formula? I look at the subscripts, 2, 2, and 4, they're all even, so I know I can reduce. I can reduce by a factor of 2. So if I divide everything by 2, I find the empirical formula is HCO2. Pb2O4. All right, well, can I reduce that? Lead, this would be lead, lead 4 oxide. Yes, I can. PbO2. All right. Here's glucose, right? We know we can do that one because we just did it. Okay, so empirical formulas are reduced versions of molecular formulas. Now, structural formulas look like this. Okay, they show the actual arrangement of the atoms. Here's another one for you. Right? This is sugar over here on the right, a glucose molecule. We're going to draw some structural formulas, nothing like these, but things like if you were to draw water, which we'll learn how to do soon, as a bent molecule with its lone pairs, that's a structural formula, right? Or this. There's another structural formula, okay? Just shows the structure of the atom. And when we write ionic formulas, we use something called the cross-charge method. Now, notice something. It's bold, italicized, and underlined, and I just drew 2 stars around it. Probably important that we know the name of this method and how we do it. So here's how you write it. You write the symbol of the cation first. The cation is a metal. It's got a positive charge. We write the symbol for the anion next. That's the negative nonmetal ion. We're going to figure out the charge on each ion based on where it is on the periodic table. We're going to drop the signs, so lose the plus or the minus, cross the charges from superscripts, and write them as subscripts. So they're going to go from the top, and they're going to cross to the bottom. So let's try one of those. We have sodium chloride. All right. So first thing I'm going to do is write the cation. That's sodium, Na. So write the symbol. Write the anion, Cl, chloride. Right? That's chlorine. Determine the charges. Okay, so remember on our periodic table, we have group 1 and 2, then we have the D block, and then we have the P block. And the P block has 6. So let's see, we got 2 there. 1, 2, 5. There we go. And there's our helium. Okay. So these guys are always +1, so +2, +3. These can be plus or -4, -3, -2, -1, and the noble gases are 0. Chlorine is a halogen. So I know that chlorine is -1. Sodium is an alkali metal. It's in the first column, so it's +1. That's how I determine the charges. I'm going to drop the signs and cross them. So the plus and the minus are going to go away. Oh, get my pin to catch up there. And we're just going to drop them down. You don't have to reduce anything here. You always reduce ionic compounds, by the way. And I don't need to write the ones that are implied. So my answer is NaCl. And that's how I take the name, right? This is the name. And I write a formula. There's the formula. There's the name. Let's do another one. Lithium oxide. All right. Same steps, right? Cross-charge method for ionic compounds. I know it's ionic because I have a metal and I have a non-metal, right? I know I have lithium and oxygen. So write the cation, write the anion, figure out the charges. All right, well, lithium is in group 1, so it's a +1. Oxygen's a chalcogen. It's right before the halogen, so it's a -2. Drop the signs, cross the charges, Li2O1. I can't reduce it. Get rid of the 1, Li2O. It's easy. The cross-charge method is super simple, right? It implies that you can do 3 things. You've got to be able to write the symbol for lithium, right, for the metal, and the symbol for oxygen, all right? You've got to know on the periodic table, +1, +2, right? This is back to our groups. We know that the D block, we can't do that. +3, plus or -4, -3, -2, -1, and the noble gases are 0. All right? It implies that you know that. If you don't know that, I'd write it on your periodic table. All right? That's a useful piece of information. Let's do one more. Calcium sulfide. All right. Cation here, the metal. Hopefully you know calcium is Ca. All right? It's on the periodic table. Really good idea to print the periodic table out and use it. Okay? You can't can't do this without the periodic table. The anion is going to be sulfur. All right. What are the charges? Well, calcium is an alkali earth metal. Sulfur is in the same column as oxygen. So +2 -2 are the charges. Drop the signs, cross the charges. I have to reduce this because it's an ionic compound. I know it's ionic because I have, again, a metal and a non-metal. That's what makes it ionic. So I can reduce this by 2. So my answer is CAS. If you didn't reduce it, you would get it wrong. So we got to make sure we follow these rules. All right. So that's how we write formulas from the names if we're using group 1 or 2 metals. Let's look about the stock system. All right. Now, notice again, this is bold and underlined, and it has italics right there. All right. And it's got 2 stars around it. You're going to want to know the name of the stock system. Anytime you have metals that are transition metals, we have to use a Roman numeral to tell the reader what the charge is. Now, here's the deal. It's called the transition block because the charges transition between like +2, +3, +4, whatever. Those, with the exception of 2 or 3 of them, they can all those metals in the D block can have different charges. Nothing else changes about how we write the formula. We're going to use the cross-charge method. Okay, we're going to determine the charge, cross them, drop the signs, reduce if we can. It's still an ionic compound. It's just now we're going to add a Roman numeral. If you don't know the Roman numerals, then you need to learn them because they're the Roman numerals, like just 1 to 10, nothing crazy. In case you've never heard about Roman numerals before, the I before V means 1 less than 5, so that's 4. V is 5. VI is 1 more than 5, like 5 and 1. All right. X is 10, so IX would be 9. The Roman numerals are still going to be positive charges, okay? And the Roman numeral tells you the charge on the cation, on the cation. This is what they'll look like. Iron 2 oxide. That's how you read that. You don't say iron Roman numeral 2. You say iron 2 oxide. That's how you read that. The formula for that would be FeO. All right, well, let's see why real quick. So I have iron and I have oxygen. I know oxygen's -2. The Roman numeral tells me the charge on the metal. So in this case, it's 2, so +2. Cross the charges. I have Fe2O2. Divide both by 2, like reduce, FeO. There it is. All right, let's do lead 4 sulfide. So here's the name. We're coming up with the formula. So you write the cation. Lead is Pb. Plumbum comes from the Latin, same word where we get plumbing, all right, because most of the pipes in Rome were made of lead, which is unhealthy. All right, the anion, sulfur. All right, determine the charges. Lead's +4. How do I know that? Well, this Roman numeral right here tells me the charge on lead. Lead's a cation, so it must be plus. So it's +4. Sulfur's in the same column as oxygen, so it's -2. Drop the signs, cross the charges. Pb2S4. Got to reduce, right? It's ionic. I have a metal and a non-metal. So divide both by 2, PbS2. That's how you do it. All right. Now, let's flip it. Let's go from a formula to a name. So when you name a compound, all right, you've got to differentiate between an ionically bonded chemical and a covalently bonded chemical. The rules are going to be different. So far, all we've seen are ionic compounds. Binary ionic compounds. Binary means 2. So this is an ionic compound that has 2 elements. It's named what's using called the suffix method. So we're going to put something on the ending. If there's a transition metal, we use the stock system and the suffix method. It's included. They're both going on. So we'd have to have a metal and a non-metal. If we're naming a covalent compound, we're going to use the prefix system. A covalent compound is always 2 non-metals. So to the right of the staircase, those compounds bonded to each other. We're going to see some of those. So let's look at an ionic compound first. So we have NaCl. So we're going to kind of flip the rules from when we wrote the formula. Now, instead of writing the symbol, we're going to take the symbol and write the name. So we're going to write the metal, sodium. Now, instead of writing the anion, we're going to write the non-metal, chlorine. We're going to change the ending of the nonmetal to "ide." Now, this is why it's called the suffix method. We have a suffix right here, IDE. IDE tells me it's just chlorine by itself. That's what "ide" means as the suffix. There is more than one suffix. You can have "ic" for acids, OUS for acids. You can have "ate" and "ite," all right, with T's. Lots of different suffixes. For now, "ide" is the one we want to look at. "Ide" means it's chlorine by itself. So NaCl is sodium chloride. And that's it. That's the end of how to name a binary ionic compound. As long as the metal is not a transition metal, you just write the metal, write the nonmetal, change the ending to IDE. Don't use any prefixes. So let's name some of these. All right. Ca is calcium. P is phosphorus. I have a metal. I have a nonmetal. This is not a transition metal. So I just write the metal, write the nonmetal, change the ending to IDE. So phosphorus becomes phosphide. So the calcium phosphide. How about SRO? Well, SR is a metal. O is a nonmetal. This is a group 2 element, so it's not in the transition metal, so I don't need the stock system. So write the metal, write the nonmetal, change the ending to IDE. Strontium oxide. Last one is obviously barium chloride, right? I have a metal. I have a nonmetal. Write the metal, write the nonmetal, change the ending. So let's look at these molecular formulas. All right, the prefix system. What is the prefix system? So if you're covalently bonded, we name you differently. That way the name tells the reader, hey, this is not an ionic compound. This is the actual, molecule. We use prefixes to indicate how many of those atoms are present. And here are the prefixes, all right? You probably learned them in geometry. Actually, I'm going to move my face up here. Okay? For the most part. A couple rules that go with us. Number one, you never use mono on the first element. That'll make more sense in just a second. And the vowels in parentheses can be dropped. So if I have one atom, we say mono. 2 is di, 3 is tri. 4 is tetra, all right? Think like Tetris, the video game, which has, I don't know if you know this, but it has 4 shapes. How about that, right? A box, a line, an L, and a T. Fun times. Anyway, it's not quad. Everybody wants to use quad. Don't use quad. It's tetra, okay? 5 is penta, like a pentagon, the government building, the Pentagon. Or if you have a 5-sided star, that would be a pentagram. All right, hexagon, heptagon for 7, octagon for 8, nonagon for 9, right? Decagon for 10. It's the same prefixes from geometry. We're just using them now in chemistry. Again, if you need to get rid of that vowel, you can avoid a double vowel. So let's look at some of these. CO2. Oh, what happened here? All right. So I write the first element. It's carbon. There's no prefix because there's only one atom. All right, I know there's only one atom because there's an assumed one. All right, the second element, oxygen. Put a prefix on it to tell me how many there are. So there are 2 oxygens. So the prefix for 2 is di. So I put di right there. I'm still going to change the ending. We're still using the suffix method. So it's not carbon dioxygen. It'd be carbon dioxide. And there it is. So write the element. If it's one of them, leave it alone. If there's more than one, we're going to put it on there. So let's go the other way. Write the formula for dinitrogen pentoxide. Well, write the symbol. I have nitrogen and I have oxygen. I know I have oxygen because I recognize oxide right there. I'm going to use the superscripts to tell you how many atoms are present. I'm going to get the superscripts from the prefixes. So di means 2, pent means 5, so I have N2O5. You never, ever reduce a molecular formula. Now, you can't reduce this one, but let's say we got N2O6. I would not reduce it. What about if we get a transition metal? Okay, let's do that. If you have a transition metal, you have to include the Roman numeral. That tells the reader what the charge is. There are two exceptions from the D block. Silver never gets a Roman numeral because it's always +1. It does not transition its charge. And zinc always gets a +2. It never gets a Roman numeral. Now, there's kind of an easy way to remember this. If you look on the periodic table, you have carbon, which is plus or minus 4. You have aluminum, which is +3. And then you have zinc, which is +2. And then you have silver, Ag, which is +1. So it makes a little staircase from carbon down. Carbon, aluminum, zinc, silver. Goes right down that list. All right, but it stops right there. Every other metal in the D block always gets a Roman numeral. Work backwards from the formula to figure out the charge on the metal so you know what Roman numeral to put. Be aware, transition metals are part of ionic compounds, so they might have been reduced. If that's the case, you have to kind of do a little algebra. I'll show you how to do that. So here we have Pb2O. So I'm going to write the metal, right? I want to write the name. So Pb is lead. It's a transition metal, so I need to put in a little space for where I'm going to put my Roman numerals. So your Roman numerals go inside parentheses. So I would just draw parentheses like that. Write the nonmetal. Oxygen is going to become oxide. We know that. We got to determine the charges on our ions. So we have to do a little bit of scratch work. Now here's the thing. We know what the charge on oxygen is because it's a chalcogen. It's in group 16. It's always -2. But lead's a transition metal. We don't know what it is, so we put a question mark there. We need to cross the charges. We need to do the cross-charge method to see if our charges match the formula that we were given. So here is the formula that we were given. We want to cross this scratch work. So this is our cross scratch work. We want to cross these two charges and see if that works. So there's our given. All right, we have uncross them. I get Pb +1 and O -2. And the question I need to ask myself is this: does that right there match the crosswork? Well, yeah, it does. Yes, so we're good. If that matches, then that means this is the right number, +1. So I'd write lead 1 oxide. Now, there's an easy way for me to check my work. We know that the Roman numeral tells us the charge on lead. So I could just write it out. Pb +1, O -2, cross the charges, Pb2O. Is that what they gave me? Yep, it sure is. I know I did it right. That's a stock problem. Let's do this one. PbO. So we went from Pb2O to PbO. So we know it's going to have a different compound here, a different formula. So we write the metal, lead. We know that we have a transition metal, right? So we're going to leave ourselves a little blank, right, for our Roman numeral. Write the nonmetal, oxide, determine the charges, right, same things. O is still -2, it's in group 16. Lead is a transition metal, we don't know. So we're given Pb1O1, so we need to uncross those charges, all right? And if they don't match when we uncross, and they're not going to, then we're going to have to solve for the original charge. So how do we change oxygen from a 2 to a 1? Right? How do I know I changed it from a 2 to a 1? Well, when I uncross this, I get +1 and I get -1. And I know that's wrong, right? Oxygen is not -1. Oxygen needs to be -2. These two things right here don't match. So I need to figure out how I reduced it. So 2 divided by x gives me 1. This is from the thing that we know, right? This is the uncrossed charge right there. There it is. That's my common denominator, right? X2 divided by 2 gives me 1. Well, if I divided oxygen by 2, I must have divided lead by 2. So we're going to call lead Y. That's the charge right here on lead. Lead divided by 2, or sorry, Pb. Wow. The charge on lead, Y, divided by 2 must also equal 1, right? Because when we uncrossed it, we got +1. So 2 divided by 2 is 1. So that charge becomes the Roman numeral. So my final answer would be lead 2 oxide. Now, these stock problems can get complicated. I mean, this is obviously one that's tough. You may want to pause it, work it out yourself. If you have questions, send me an email. We can do a Google Meet, something like that. See if we can't figure this out. Okay, but these are the hardest ones that we'll have. Here are some things for you guys to name. All right, don't go to the next slide. Name them first. Notice all of these are stock system questions. All right, all of those metals come out of the transition block, so they're going to have Roman numerals. Here are the answers. Make sure you get those answers. All right, so that's about it for this part of naming. We're going to have one more little video on polyatomic ions and the diatomic molecules, but name stuff. If you don't name stuff, if you don't practice naming stuff, you won't be any good at it. So go and name.